All right, last one. Let's talk about 4.6. This is the last part of the first part of pre-calculus. Let's talk about solving basic equations, specifically exponential and logarithmic equations. So far, we've learned how to use properties of these things, we've learned how the logarithms behave, we've learned how exponentials behave, but we haven't talked about the relationship between the two. I mean, we have, but we haven't directly stated this. So in case you haven't figured this out yet, log base b of x and b to the x are inverse functions. That is, by definition, for any base well-defined and a real number x greater than 0, the log base b of b to the x and b to the log base b of x is x. That is, the functions log base b of x and b of x are inverses. Remember, the definition of an inverse is if you can plug one function into another and then the other into the first, and you get out x both ways, they're inverses. And I'm telling you, that's exactly how they work. So, using this, we're able to solve examples like this first example here. It says solve 11 times 2 to the 3x power equals 1, rounding to the nearest hundredth. Now, we haven't had any luck with this in the past, trying to solve these sorts of things. If you tried to use these using any fact other than this inverse fact that I just taught you, you wouldn't have much luck. We don't really know, or at least haven't up until now, known what to do when the x is in the power. If it's a nice x, and it was a nice thing that was equal to, we could try to guess, I guess, and sometimes it works. If we were trying to solve, for example, 2 to the x equals 8, we can solve that in big air quotes because we know that the answer is 3, because 2 to the third is 8, and we can rewrite it as a logarithm and kind of think about it a little bit. But that's only when the numbers are nice. In this case, the number really isn't nice. So the first step in all of these, and you may want to write this down, but the first step in all of these is just to get the exponent or the log by itself. Get everything over to the other side. So right now, there's an 11 being multiplied by this. So the first thing I'm going to do, of course, is just write all this down. So it's 11 times 2 to the 3x equals 1. And that's just going to get turned into, we're going to divide both sides by 11. So 2 to the 3x equals 1 over 11. So that's the first step. Now, what we're going to do to get rid of this base 2, well, it says it up here. It says to get rid of a base 2, you can just take log base 2 of both sides. So all we're going to do is just take log base 2 of both sides, because the base is 2. If this were a 3 that I just circled, we'd take log base 3. If it were an e, we would take the natural log of both sides. That's all there is to this. So we're going to take log base 2 of 2 to the 3x. Might want to put some parentheses around that. Equals, and if you do something to one side, you've got to do it to the other. Log base 2 of 1 over 11. Okay? So that's all we've got to do there. So now we'll notice something real quick. Log base 2 of 2 to the 3x, well, the log base 2 of 2 to the something cancels. And all that you're left with on the left side is just 3x. And I know that it doesn't feel like that's how that should work. It feels weird that the exponent suddenly becomes not an exponent anymore, but it's exactly how it works. Look, there's a b here, there's a b here, and all that's left is an x when you get done with it. It's exactly how it works. And on the right side, well, that's just a constant. It's a weird constant, which is why you're asked to find it to the nearest hundredth. But it's just log base 2 of 1 over 11. That's just a number. Log base 2 of 1 over 11. It's just a number. So just leave it like that. So we'll come all the way back down here, and we'll begin again. So we'll kind of snake this all the way back down here. And right here, we'll go ahead and finish this problem. So all we have to do now is just divide both sides by 3. So let me move down here for a second and get us a little bit more space. There we go. So now all we have to do is just, we've got 3x equals all that. We're just trying to get x by itself. So your final answer will be x equals log base 2 of 1 over 11. And then we divided everything by 3. And all that remains, since it asked for it to the nearest 100th, I'm usually okay with this sort of thing. But if for whatever reason you're asked to find it to the nearest 100th, you just shove this into a calculator, exactly like it says it. I recommend Desmos. Go to Desmos, type that in. If you want to type this in exactly, log base 2 and all that, you'll write it like this in Desmos. You'll do log underscore 2. And then you'll probably need to hit the right arrow or space to get back up in here. Parentheses 1 divided by 11. And then another division symbol, and then 3, and it'll write it out for you. The underscore, by the way, is shift plus the thing beside of your 0 key will give you this. And that will give a subscript. So shift plus the key next to your 0 key, which is normally the minus key, will give underscore. And if you want that, and that does subscripts. If you want to do a superscript, like an exponent, that's shift plus. And when I say plus, I don't mean the plus key. I mean hold down shift and also hit 6. And it'll give you a caret. It'll give you a caret like that. And that will be super useful for you. So let's go on and look at a few more of these. So here's a couple more. Let's solve 12 times 10 to the x over 2 equals 1. And we're going to round this to the nearest hundredth as well. So I'm just going to write this again. 12 times 10 to the x over 2 equals 1. The first step in all of these is get rid of everything that's being multiplied by it or added or subtracted to it. So we're going to do 10 to the x over 2 equals 1/12. I divided both sides by 12. And then from there, all I'm going to do is take the log base 10 of both sides. Just the log base 10 of both sides. So I'm going to write it in your notes, but I usually skip this step when I'm doing it myself. So it's the log base 10 of x over 2. Now, I didn't write base 10. You can write base 10 if you want to, but that's exactly the same as just writing log. Remember, that's the same thing. Log base 10 and just the normal log from the last video. It means exactly the same thing of 1/12. Okay, well, log base 10 of 10 to the something, log base 10 of a base 10 is just whatever is up there. So all we're going to do here is all that's left on this side is x over 2. Equals log base 10 of 1/12, like that. And then all that remains is just multiply both sides by 2. So x equals 2 times log base 10 of 1/12. And that's not the answer. This thing wants you to do it rounding it to the nearest 100th. So all you have to do is go to Desmos, shove this thing into a calculator, and you're done. That's it. Shove this thing into a calculator, round to the nearest 100th. I have faith that you can do that. But that is the answer. And we normally leave it like that, just like this is fine for me. But if the instructions say to round it to the nearest 100th, you better shove it into a calculator. I don't know what log base 10 of 1/12 is. It's a ridiculous number. It isn't going to divide nicely. It isn't going to work out nicely. It's going to be some transcendental thing that I'm never going to be able to know. So just go throw it to a calculator and see what you can do. Be very careful with it. All right? Let's look at this next example. E to the 5x equals 20, rounding to the nearest 100th. That's fine. E to the 5x, this is an easy one, equals 20. So all I'm going to do on this is I'm just going to take the natural log of both sides. So you could say take log base e of e to the 5x equals log base e of 20. You just took the natural log. There was nothing in front of this to get rid of, so I didn't have to do anything with it. But we don't write log base e. Remember, the log base e, and I'll let you remember this over here, the log base e of x is the natural log of x. It's written ln x, like that. We use this notation always, forever. This will make me angry. This will make me very happy. Angry, happy. So let's do the happy thing. So we're going to take the natural log of both sides. So the natural log of e to the 5x equals the natural log of 20. And that's going to turn into... So the natural log of e to the 5x, those cancel. You're left with just 5x on this side, equals the natural log of 20. The natural log of 20 is just a number. It's a ridiculous number, but it's just a number. And now all we have to do is just divide by 5. So x equals the natural log of 20 divided by 5. And if you type this into Desmos, it will give you a number. Round it to the nearest hundredth and type that number in, and you'd be done, if this was the problem. The way I would give the problem to you, if I were going to give it to you on a sheet of paper, would be just solve this, period. And the answer that I put in the box is the answer. X equals natural log of 20 over 5. That's the exact thing. You're going to give an approximation if it asks you to round to the nearest 100th. But that's how to do both of these. So just using the property that the natural log and e are inverses, or that log base b and b to the x are inverses, is all that you're doing in these. This is exactly like how you were taught to solve when you found the relationship between square roots and squares. It cancels them and gets rid of them, and that's close to how it works. There's the plus or minus thing because of the domain restriction and all that, but we've already been over that. So there's how to do a couple of those examples. So let's just move on and do a bunch more of these. Why not? So let's do another example. It says solve 3 times the natural log of 8x plus 8 plus 11 on the outside equals 20. Okay, we're trying to find the value of x that makes this work. So be very careful with these when you go through and do them. Remember that the natural log is just log base e. Keep that in the back of your head. And also don't lose track of any of this. You want to get rid of all of the stuff off of the logarithm or the exponent before you do the inverse. So there's a plus 11 and there's a times 3. If you were trying to solve, think in your head like this whole thing here is x. This whole thing is your variable. Okay? If this were 3x plus 11 equals 20, how would you solve for just the x? Well, you'd subtract the 11 and divide by the 3, right? So subtract the 11 and divide by the 3, then deal with the natural logarithm. That's all that you're doing. So treat that whole expression, whether it's exponential or logarithmic, treat that whole expression in the box like it's its own variable until you get it by itself, then break it apart. It's like a 2-step process. So I'm going to write this out. That's always the first step in these. So 3 times the natural log of 8x plus 8, all right, plus 11. And be very careful with that. Okay, don't try to add together the 8 and the 11. The 8 is inside the natural log, the 11 isn't. So I'm going to subtract 11 and get 9, and then I'm going to divide by 3 to get 3. And I don't think that that's going to throw anyone for a loop. If you want to put all of the steps in your notes, hey, go for it. But you're left with this. Okay, I subtracted 11 to get 9 and then divided by 3. So I'm to that step. So once you get to this step, now the natural log is alone by itself. So remember, the natural log is log base e. That is, we're using this fact. We're using that the natural log of 8x plus 8 is notationally equivalent to log base e of 8x plus 8. Just keep that in the back of your head. So if you want to get rid of the log base e, then you're just going to take this whole thing and make it as a power of e. That is, you're going to, this is going to become the power of e on this side, and this is going to become the exponent for e on this side, just like this. E to the natural log of 8x plus 8 equals e to the third power. That's all that we're doing with this. It looks really weird, but it looked really weird going the other way too. But that's all that there is to this, because e and the natural logarithm are inverses. Because remember, the natural log is just log base e. So those will cancel, which will leave you with, on the left-hand side, 8x plus 8. On the right-hand side, e to the third. Remember, e is just a number. It's about 2.718. Well, a number to the third power is just another number. This whole thing over here is just a number. So just treat it like a constant. That's all you got to do. So let's divide this. Let's bring this up. Let's finish it out. So we've got 8x plus 8 equals e to the third. That's a transcendental number, just like pi. It's not going to combine with anything nicely. But we're going to subtract 8 and divide by 8. That's pretty clearly how we're going to finish this problem out. So we're going to get 8x equals e to the third minus 8. And then we'll finally finish with x equals e to the third minus 8 over 8. And that is the exact solution. So the way that this is asked, it wants you to type this exact thing in right here. The whole thing, exactly like that, e and all. If it says round to the nearest hundredth or something, then type that into Desmos so that it looks exactly like that, and then round to the nearest hundredth and you're done. But that's all that there is to it. This step right here is the key. And all that we're doing in this entire section is just using the fact that the natural logarithm and the exponentation, they're just inverse functions of one another. They undo each other. That's all that we're using. In this next example, we want to write log base 4x of 2x minus 2 equals 5x as an exponential equation. And this is just another way to do that same thing that we've done like 6 billion times. It's the base raised to this power equals what's inside of this. That is, it's the base, in parentheses, raised to what was on the other side equals what was inside the logarithm. That's the whole thing. Write it as an exponential equation. Bam! There. It's an exponential equation now. Looks ridiculous, but it's true. That's the way that it works. It's the exact same thing. I'm not going to do a bunch of these examples. I'm just going to do this same one again for you. So, take the base. Write the base. Hop across the equal sign. Take literally everything over here and raise it as a power. Make sure to put this whole thing in parentheses so that it's correct. Once you've done that, write your equal sign, hop back across the equal sign, and write everything that was the input to the log. You're done. It doesn't matter what it looks like. Just trust yourself and write it. The most important thing is these parentheses. There's a big difference between 4x to the 5x and 4x to the 5x. Those are not the same thing. In this example, you're only raising the x to the 5x, then multiplying by 4. In this example over here, this part right here, this is equal to 4 to the 5x times x to the 5x. You're raising each thing to the 5x. There's a big difference. So don't make that mistake. What I'm saying is write the parentheses around whatever the base was. That's the thing that's going to get you if anything gets you. That's all there is to this. I don't want to spend any more time on it. So for these last few problems, I want to look at them directly, but they look like this. What are the features of the function f of x equals 2 times 2 to the x minus 5? And then the other one is, what are the features of the function f of x equals 2 times log base 3 of x plus 4? And this is just taking everything that we've learned in all of the last chapter and putting it all together. So I'll give you a warning. This is about to blow your corneas out in about 3, 2, 1. There we go. So I apologize for that being so ridiculously bright there, but that's just how it is. So let's look at this for just a second. So it says, what are the features of 2 times 2 to the x minus 5 graphed below? So you look at this thing and you see that there's some features going on here, and then you see this big wad of text down here. So I'm going to scroll down a little bit, and it wants you to fill out all of this. Okay, so the function f of x is that an exponential or a logarithmic function? If you look back up at its form, it's pretty obviously an exponential function. It has an exponent. So it's an exponential function. You get that by just looking at that. With a. Now remember, exponential functions always have horizontal asymptotes. Logarithmic functions always have vertical asymptotes. That's always the pair. You'll never be able to answer this, and you'll never be able to answer this either. So this is an exponential function with a horizontal asymptote. Where does the horizontal asymptote look like it is? Well, if you look down around -5 here, you'll see that seems to be where it's laying down at. Remember, so it happens at -5, and what's locked? The height is locked, right? It's always y equals -5. The height, y, is always locked. That is the equation for a horizontal line is y equals, as in y. X can be anything it wants to, so it can be the entire x-axis, but y is locked always at -5. So that's the first sentence. The function f of x is an exponential function with a horizontal asymptote of y equals -5. Horizontal asymptotes always look like y equals, and then -5 is just the point it goes through on the y-axis, all right? The range of the function, that's all of the values that it can take on as it gets out. Well, pretty clearly, if you look at this, if there's an asymptote at y equals -5, for the range, you're looking at the y-axis, well, there's nothing below -5. So the range of the function is, and then you've got a big old box here. Let me scroll down here so you can see all of it. Here's all of your options here. And you can see, if you look back up there, that it's everything from -5 up. So it's everything from -5 up. That's this one. And notice that they're very nice to you. I would have been meaner than this and put in some square brackets as well, but it's parentheses on both sides. And the reason that it's parentheses for the -5, obviously, is it's an asymptote. It never gets to the point. to be equal. So that's the range of the function. So look at this function and convince yourself that it's -5 to infinity. The range, the set of y's, is everything positive, but the smallest it ever gets is -5. Okay? And then the other options are, and it is increasing or decreasing on its domain. Well, look at its domain, and you always read left to right when you're looking at increasing or decreasing. So is it increasing or decreasing? Well, as you go from left to right, the number, the curve itself, is obviously getting larger. Look at it. It shoots off to positive infinity real quick. So it's increasing on its domain of, and remember, exponential functions have a domain of all real numbers. Exponential functions have a domain of all real numbers. Logarithmic functions have a range of all real numbers. And then it just wants you to do the end behavior. And that's easy as pie. The end behavior on the left side is as what? Okay, so the end behavior on the left side. So as we approach, as we go off towards the left, it says as x approaches negative infinity, because our x's are able to go to negative infinity, our y values, they're going to hug in on -5. That's what the end behavior is. It doesn't go off to negative infinity. In order for this line, as you go to the left, to go off to negative infinity, you would have to actually be going down. You're not going down. You're going left. You're hugging up to -5. You never get smaller than -5. You said that up here when you picked the range to be this. The end behavior on the right, however, is pretty clear. As x goes to infinity, y goes to infinity. So as x goes to infinity, y goes to infinity. That's pretty clear on the right. That looks like every x squared function I've ever seen. And that would be the answer to that. If you submit it, you would get it correct. And that's a lot of stuff to know about this, but I love these problems so much, and the only way that you get good at it is just doing a lot of them. Of course, the help on this is fantastic, but I love these problems because it makes you think about all of the things that you've learned about this so far. So that's that one. So let's take a minute and let's look at another one of these things. This one wants us to talk about what are the features of the function f of x equals 2 log base 3 of x plus 4. So that's what the graph of 2 log base 3 x plus 4 looks like. And it's pretty clear that this is a logarithmic function because there's a log. Like, okay? So when we scroll down, the function f of x is that it's a logarithmic function, obviously. Okay, and all logarithmic functions have vertical asymptotes. All vertical asymptotes look like x equals something. So we've got all that out of the way real quick. That's just by looking up here at whatever this was. I'm not even looking at the graph. I mean, I know that that's a logarithmic function just by looking at it because I've done it a lot, but it's very clearly logarithmic because I've got it's right there. It says log, so it must be logarithmic. If it's logarithmic, it always has a vertical asymptote. Vertical asymptotes always look like x equals something. So go find the vertical asymptote that it looks like this thing's hugging up to. So look on it, it looks like about -4. Up and down, right here at -4. Imagine that line. So that's going to be it. That's it. That's all there is to that. So we'll type that in. Now, the range of the function is, well, it increases very slowly. So it very obviously it goes down to negative infinity real quick. But the logarithmic function increases as slowly as the exponential function does quickly. So it does actually eventually get to, quote unquote, get to infinity, like it gets as big as you want. You've just got to go way super far out for this thing to get big. But it will eventually get big. There's no horizontal asymptote on this, even if it looks like there is. If you kept scrolling to the right, if you take this function and plot it on Desmos, and I encourage you to do this, go plot 2 times, just the natural log or log base 10 is fine. It doesn't change it that much. But 2 times log base 10 of x plus 4, and then just scroll way off to the right. I'll bet you that you can get that number as high up there as you want to. You just have to scroll way, way out to the right in order to do it. But there is no horizontal asymptote on these. These things only ever have vertical asymptotes, and they always have vertical asymptotes. Logarithmic functions do. So the range of all of these functions is always everything. So we're just going to select that. Okay? And then look at it. As you read it from left to right, it's clearly increasing because it's clearly increasing. If you look over on the right there, it's clearly pointed up. It's not pointed up by much, but it is a gentle slope going up. And you always read increasing or decreasing from left to right, just like you read a sentence. So it's increasing on its domain of, its domain. Its domain is the list of things you're allowed to plug in. Well, I can plug in any number bigger than -4 and we're fine. Just look there at the x-axis. Look along the x-axis, and as you're looking along the x-axis, look up and down. The parts of the graph where it has a domain is the parts where there's actually a curve above and below the x-axis. You can see, however, to the left of -4, there's nothing there. So it's not defined there. If it's not defined, it doesn't have a domain. So it has a domain of, well, everything bigger than -4. So how do you say everything bigger than -4? Here's all your choices. Everything bigger than -4 looks like that, right? This is everything smaller than -4. Don't pick that. That's everything up to +4, but +4 isn't even important to this thing. It's everything bigger than -4 is going to give you your domain. And the last thing is just the end behavior. The end behavior on the left side is as your x's approach. Now here's the deal. You can't select this. That's not true. On the left side, your end behavior, so read it from the right to the left. Read it from the origin on out. As you approach -infinity, you can't approach -infinity. You never get to -infinity. There's a wall that goes straight through x equals -4, and you can never get to -infinity. You can't even get past -4. You definitely can't get to -infinity. So you can't pick that. You have to pick -4 from the right. And what that means is you're coming in from the right. And we'll talk about limits when we get to calculus. But that's the sort of thing you're thinking about. So it's as x approaches -4, the asymptote from the right. Then we'll look at the other part is what's your axis, what's your curve doing? Well, it's going off to -infinity. Clearly, it just drops down straight through the floor. Okay, it doesn't approach -4 in the y direction. It zooms way past -4 all the way to -infinity. And then on the right side, well, it's slow about it, but it does actually get to infinity very slowly. And it does actually get to infinity very slowly. That's the thing about logarithms. They are slow. But you can get as big of a number as you want out of a logarithm. You just have to put a exponentially larger number into its input. And that would be the answer to that one if you wanted to go look at it. So that is one example of each one of these kinds of problems, and the only way that you can get good at these is thinking about them and working through them. So I invite you to do that. So by all means, do that. And then let's finish up the entire year. The entire semester, this entire first part of pre-calculus here, by talking about the one-to-one property of exponential equations and using it on a very simple thing here. So for any algebraic expressions s and t, if any positive real number b equals 1, we have that b to the s equals b to the t if and only if s equals t. That's it. That's all that it is. And you may as well pretend like that was a lowercase b. But if and only if s equals t. That is, two exponential expressions with like bases can only equal each other if their exponents equal each other. That's it. So the way that this works is, look here. We solve 4 to the 5x plus 4 equals 2 to the x minus 12. Okay? These are not like bases, but the trick to this is, well, you can write these as like bases, right? You can write 4 as 2 squared. 5x plus 4 equals 2 to the x minus 12. 2 to the x minus 12, I said. So if you're going to do it this way, remember that raising a power to a power, you just multiply. So this is 2 to the 2 times 5x minus 4 equals 2 to the x minus 12. And now they do have like bases. And using this one-to-one property up here, we're just going to say, well, they have like bases. Well, the only way that that can happen is if 2 times 5x minus 4 equals x minus 12. And then from there, it's just basic algebra to solve it. So this is 10x minus 8 equals x minus 12. I'm going to add 8 to this side. And I'm going to get negative 4. I'm going to subtract an x over to this side, and I'm going to get 9x. And then I'm going to get x equals negative 4 over 9. Negative 4 over 9. And that's the power. That's the power that solved this original thing. Negative 4 over 9. And I just used the property when I came from this step to this step. That's all that it's saying. Get like bases however you want to. Remember that when you raise a power to a power, you multiply the powers, and it's multiplied by all of this stuff, so you have to distribute it eventually. And go ahead and go through this. Some of the most basic examples of this actually gives it to you like this to begin with. And if the bases, the things, big things down here, are exactly the same, well, just, hey, set the powers equal to each other and you're done. And that makes sense. If you're going to raise something to a power and raise another something to a power, and if it's the same base, then yeah, the only way they're going to equal is if their exponents are equal. So yeah, I'm okay with that. And I'm also okay with that being the last example of the first part of precalculus here in math analysis. So I'd say see you in the next one, but I can't say that. If you plan on going through and seeing trigonometry, then yeah, sure, I'll see you in the next one. But otherwise, hey, you take care.